Okay, let's dive right into this explainer. We're going to take a factory tour of exactly how generative AI transforms your raw text into a finished prediction. We hear about AI all the time, right? But today, we're actually going behind the scenes. We're going to look at the gears, the math, and the literal mechanics that make these incredible systems tick.
Here's our quick roadmap for the tour. 1. Foundation models explained. 2. Step 1. The input. 3. Tokenization, words into numbers. 4. Word embeddings and context. 5. The decoder predicts output. And 6. The transformer advantage. Let's get into it.
Section 1. Foundation models explained.
So the crucial point here is that foundation models are exactly what they sound like, a foundation. These are massive, pre-built machine learning models. And when I say massive, I mean developers basically crawl the internet and feed the model terabytes upon terabytes of generalized text, images, and all sorts of multimodal data. The model uses this sheer volume of unlabeled info to build a giant foundational repository of knowledge with literally billions of parameters. Because it has such a deep, rich context of the world baked right in, you can adapt it to do almost anything.
Thanks to all that massive pre-training, these foundation models generally fall into 4 core capability buckets that can seriously streamline operations and save a ton of time. They can generate code directly inside your development environments. They can generate content. We're talking everything from a quick blog post to high-quality marketing art. They can summarize dense, long-form articles or heavy reporting data in seconds. And of course, they power those question and answer chatbots we're all super familiar with by now.
Now, this brilliantly illustrates why foundation models are so uniquely powerful. They rely on unlabeled data. Think about the alternative for a second. Labeled data requires a whole human task force sitting down to create laborious annotations. Like someone literally has to look at an image and manually tag it with the word dog. It takes forever. Unlabeled data, though, that's just raw information scraped right from the internet. It's highly scalable. During pre-training, the model just ingests all this raw text, automatically learns the context, and tracks the relationships between words entirely on its own. It's a completely autonomous learning process, which is wild when you think about it.
Section 2. Step 1. The input.
All right, here is our raw material. A puppy is to dog as kitten is to... Now think about how you instantly solve this puzzle in your head. Your brain just effortlessly recognizes the relationship and fills in the blank, right? Well, today, we're going to see exactly how a machine solves this exact same puzzle, completely mechanically, step by step.
Section 3. Tokenization, words into numbers. Okay, so a machine doesn't read English, right? It reads math. Let's break this down. Step 1. The model breaks our input sentence into smaller, standardized parts called tokens. That could be a whole word or just a single character. Step 2. It standardizes all that data. And then step 3, and pay attention because this is absolutely crucial. It encodes them. It actually converts those text tokens directly into numbers. So a classification marker becomes a number like 101. The word A becomes 1037. This conversion from words into numbers is the fundamental baseline requirement for the AI to even begin processing our puzzle.
And you know what's really fascinating? These tokens aren't just some technical necessity. They are basically the fundamental financial units of AI compute power. Because every single token requires computational power to process, the sheer number of tokens you feed into a model directly dictates its cost. Seriously, when businesses scale their AI operations, they are quite literally counting the cost in tokens.
Section 4. Word embeddings in context.
Once we have our numbers, the AI needs to actually understand what they mean. To do this, the transformer embeds them into what's called an n-dimensional vector space. Just imagine a massive, multi-dimensional map. Every single token gets a specific set of numerical coordinates on this map. And here's the clever part. Words that share similar meanings are plotted closer to each other. So the coordinates for cat and feline are clustered tightly together, whereas dog and kitten are plotted much further apart. By mapping out our tokens this way, the AI can mathematically calculate the physical distance between words. That is exactly how it grasps the actual context of our sequence.
Section 5. The decoder predicts output.
All right, this brings us to the climax of our factory tour. This is the exact mechanical step where the decoder predicts the final output. First, it grabs those vector coordinates from our map. Next, using built-in mathematical mechanisms, it evaluates the relationships. It calculates the exact mathematical distance between the puppy vector and the dog vector. Finally, it takes that exact distance and literally applies it starting from the kitten vector to figure out what the missing word should be. And the decoder doesn't just randomly guess, right? It calculates probabilities. The model generates a list of potential output words and assigns a mathematical score based entirely on those vector relationships we just talked about. It looks at the coordinates. Cat scores a 9.2, bird gets a 5.5, and bear gets a 4.7. The AI just follows the math and selects the word with the absolute highest probability.
Section 6. The Transformer Advantage.
So, based on that highest probability calculated by the decoder, the model outputs its final prediction. It generates the next word and gives us, a puppy is to dog as kitten is to cat. The machine has successfully completed our input sentence, arriving at the exact same conclusion a human brain would. But it did it entirely through tokenized vectors and probability math. How cool is that? Now, the secret sauce that makes this entire factory so incredibly fast is the transformer architecture itself. See, older machine learning models, like recurrent neural networks, were forced to process text sequentially. They had to read one word at a time, moving painfully slowly down the line. Transformer models, however, are highly parallelizable. They process the entire input all at once during the learning cycle. They look at all the tokens and all the relationships simultaneously. Combined with thousands of hours of fine-tuning, this parallel processing is exactly why these models can give you such reasonable, accurate answers almost instantaneously.
And that concludes our explainer tour. You've seen exactly how raw text is broken into tokens, converted to numbers, plotted on a multi-dimensional map, and then decoded using pure probability. Generative AI isn't magic. It's just incredibly fast, highly parallelized math. Understanding this mechanical process gives you the power to use foundation models so much more effectively. So now that you know exactly how the gears turn, what complex puzzles will you ask a foundation model to solve next? Keep experimenting.